Students, so I'm back with another video, and in this video we are covering multiple questions, and some of are organic, some of are inorganic. I'll be coming up with solutions of physical chemistry questions as well from the sample paper, and today we are taking up a few questions, and we'll start with question number 13 and 14. Now in question number 13 it says the compound is given and the compound is subjected to Gelder's method for estimation of nitrogen. Now what happens in Gelder's method is the compound is converted into ammonia, and the ammonia is titrated with an acid, typically sulfuric acid. And in some cases the extra sulfuric acid is then back titrated with NaOH. The amount of NaOH used gives us the excess of acid, and from the original amount of acid and we subtract the excess, that gives us the amount of acid that reacted with ammonia. Therefore, from there we get the amount of ammonia present or released on the Gelder's method determination process, and from there we get the percentage. So this is the outline of the estimation of nitrogen in a compound using Gelder's method. And a point to be noted in this process is that um, nitrogen present in rings, like in case of pyridine, here, like here in the compound X, or in cases of azo or cases where NN double bond is present, those cases, or rather those nitrogens, do not participate in the Gelder's method for the estimation of nitrogen. Hence, in this compound, from 1 mole of the compound X, we get 2 moles of NH3. So, and the amount of substance given, X, and the question is 2.21 gram, that is precisely 0.01 moles of the given compound. So from 0.01 moles we get 0.02 moles of ammonia, and therefore the mass turns out to be around 0.34. So this was the answer key that was been released by the board. Now in the second question, question number 14, it is given that X, Y, Z are 3 atoms of 3 non-metallic elements belonging to the period 2. Now the nonmetals of period 2 typically include boron, carbon, nitrogen, oxygen, and fluorine. Now the data given is that the covalent radius and the first ionization enthalpy are increasing. The covalent radius is increasing as we move from Z to X to Y, or rather from X to Y to Z, the covalent radius is decreasing, and the ionization enthalpy has been given as Z greater than X greater than Y. So the middle one has ionization energy less than the other two, and the electron affinity of Z is the highest. So as we move from left to right, the electron affinity increases. Now this pattern exactly fits the data of nitrogen, oxygen, and fluorine. If we retrospect, we see that the fluorine has the smallest covalent radius, followed by oxygen and then nitrogen. The electron gain enthalpy, or the electron affinity, of fluorine is the highest, then oxygen, and then nitrogen. And the first ionization enthalpy of nitrogen is greater than that of oxygen, but less than that of fluorine. So if the atomic number of X, Y, and Z are n minus 1, n, and n plus 1, rather in this case Y is oxygen, so the atomic number of oxygen is 8, which is the value of n. So the answer shall be 8. Now for the last question of today's video, we are taking up question number 12. And this is again a very fundamental question, nothing too much to think. And we are given a compound P which has multiple OH groups and a aldehyde group, and it is heated in the presence of HI. Now this is a very popular reaction that has come up many times earlier in the examination as well, and on heating with HI we just get back the carbon skeleton with all the CO bonds reduced. So what we get here is 1, 2, 3, 4, 5, 6, or hexane. So our product Q is hexane. Now, when we read the question further, it says that A, B, C, D are four structural isomers of Q. So let us draw the four structural isomers of Q first. So this is 1, this is 2, this is 3, and this is 4. So these are the four structural isomers possible of n-hexane, that is 2-pentane, 2-methylpentane, 3-methylpentane, 2,3-dimethylbutane, and 2,2-dimethylbutane. Now, it's been given that the boiling points are in the descending order, and when we see the boiling points of these compounds, we find that boiling point of A is the highest, although it is comparable with B, then comes in order C, and then comes D with the highest branching. Now, the point to be noted here is the difference between the boiling points of A and B and C and D are not very significant. They might be of just the order of 7 to 8 degrees, but there will be a small difference surely. Now, even if we don't compare between the boiling points of A and B, we surely know that the boiling points of A and B will be greater than that of C and D. Now, we have to compare between C and D to get the isomer that is in third position, because that is the isomer that we are talking about in this question further. So, when we compare between C and D, we observe that in case of D, the branching is a bit more as compared to C. That is, there are two methyl groups on the same carbon atom, and therefore the area reduces by just a fraction more. And therefore the melting points, or rather the boiling points, the boiling points of C is just a bit higher than that of D. So C is the required compound, or it is in this case 2,3-dimethylbutane. Now, to proceed further with the question, it is given that this compound C, or 2,3-dimethylbutane, is monobrominated, and we have to give the number of possible isomers. So this is one case, and this is the other case. We get only two cases on monobromination, and the second case that I'm drawing right now shall be the major product. Now, when we compare or when we count the total number of isomers, we have to take into account that this compound has a chiral center, and therefore it shall be in an enantiomeric form, and so this contributes 2 isomers, and this is just optically inactive, so it contributes 1. So this final answer shall be 3. And if you verify it with final answer key, it turns out the answer is 3. So this was all for today's video. Do tune in for more such videos and solutions to come up for this paper, and keep learning.